Okay, we'll continue to discuss general solution of the Laplace equation, which we found by solving Laplace equation using separation of variables in polar coordinates. So then we found the solution in this way. So this is solution of Laplace equation. In polar coordinate, r is a radial coordinate and theta is azimuthal angle. And then the solution can be written in the following way. One to infinity an. This is in 2D. And then we had probably, the coefficients that I am writing here might be a little different from what I wrote before. But anyway, basically, we have a combination of many terms, and this guy is infinite series. And last time, we dropped some of terms by imposing boundary condition at infinities. So, for example, this guy, an is 0, except n equal to 1. So if n is greater than equal to 2 or greater than 2, then a sub n is 0. The reason is, likewise, c sub n also 0 if n is equal to 2 or greater than 2. The reason is, when we compute velocity, which is a physical quantity that we have, is, first of all, the velocity can be written in this way. Radial and the tangential velocity can be written in this way. And for these other physical quantities, they have to remain finite everywhere, including infinities. So if n is 1, then when we take a radial derivative, it's constant. But if n is greater than 1, then the velocities become infinity as r goes to infinity. Okay, so that's why we impose these conditions. So this is for ur and u theta to be finite as r goes to infinity. Okay. So these velocities have to be finite as r goes to infinity. Therefore, these guys and these guys are equal to 0. Because n equal to 1, we have r cosine theta. So for n equal to 1, we have a1 r cosine theta and b1 r sine theta. So when you take r derivative, or when you divide by r, these are finite values. And this represents, this is a x and this is y. So this is a uniform flow in the x direction, and this is a uniform flow in the y direction. And then we looked at some of these terms, right? So n equal to 2. Before I talk about that, let's look at these terms. And this is constant, so it doesn't matter whether we have or not. When you take a derivative, this guy vanishes, so we don't have to worry about it. And then we looked at this guy, although we haven't looked at these two. So last time, we looked at this guy. This is phi, and then we realized that this is nothing but the velocity potential for a source, because phi, when I take radial derivative, and then I end up with 0, no, 1 over r. Okay, this is a velocity potential for a source, and when you take r derivative, we'll get this, and this is a radial velocity, and the tangential velocity is given by d phi d theta, and this is identically 0. So meaning that we have a radial velocity which decays 1 over r. So as you move away from origin, the velocity decays. So radial velocity decays like 1 over r, but we don't have any tangential velocity. So we have a flow like this. So there is no theta dependence, but it depends on r. So where you are. So if you see r, then the velocities everywhere on this circle is are the same. If you draw another circle, of course, then you have only radial velocity as well. But these velocities are, much smaller than velocity here because it decays, as 1 over r. But there is no radial, no tangential velocity. So this is we call source. And last time I made a connection between B naught and the mass flux, and which is Q divided by 2 pi, and here Q is actually volume flux because we didn't multiply by rho. So a volume flux was defined like U R d theta, okay, from 0 to 2 pi. So what you're doing is you multiply radial velocity by circumference, and that's what you do. And then that's how much water is coming out per unit time, and so we made a connection between the volume flux and this constant B naught. So this is a source term, and also if we had a negative sign for B naught, then it's a sink instead of source. Yeah. So in that case, flow is moving into the center instead of moving out. Okay. So now let's look at these terms. So these are gone now, except n equal to 1. Okay. So these are gone, and then we'll look at this guy and this guy. And n equal to 1, that's particularly we are interested in. So phi, in this case, a b1 divided by r cosine theta, or d1 divided by r cosine theta. And so from here, you can find radial velocity and the tangential velocity. This time, you do have both radial and the tangential velocity components. And to make this formally, to make these solutions formally from source and sink, what we did was we put source on the left hand side and sink source here and sink here, and then we move, these two singularities toward, the center. Okay, but we have to take, some limit such that the distance times, this q to be finite, and then we can construct, these solutions. Okay, so if you put, source and sink on the horizontal axis, and then let this guy move toward each other, then we could generate, this. Okay, so this is a dipole solution. And the other way to do is, put source here and sink here, or source here, sink here, it doesn't matter, only the sign changes. And then you make it move. Okay? And then you generate, flow like this. So when that happens, the dipole is sitting here. On your left-hand side, you have source, you have flow like this. Okay? Coming out and going back to sink. So that's the, flow pattern of dipole. When source is sitting here, sink is sitting here. On the other hand, if you have a source at the bottom and the sink on the top, then you generate flow like this. Okay? And in terms of Cartesian coordinates, you can write this as B1. I multiply denominator and numerator by r, then I have r cosine theta and r squared, which is B1 x squared plus y squared and x. On the other hand, for this case, I have phi b d1 r cosine theta, and then I have d1 y x squared plus y squared. Okay. So this is the velocity potential for dipole aligned in the y direction, and this is dipole aligned in the x direction. That's what we discussed last time. Also, we call these solutions these also singularities, because the velocities diverge at r equal to 0. So the r equal to 0 is a singular point, but it's okay. Typically, we place these singularities inside of a body to represent the flow around the body. So r equal to 0 is not in the domain, fluid domain. Therefore, even though something blows up or something is infinity, that's okay. So as an example, we consider flow around the circular cylinder, and then in this case, the r equal to 0 is sitting here. So what we do is we place the dipole here. Right? So we place a dipole here, which is aligned in the x direction. That's what we have. This should be sine theta. So we aligned the dipole in the x direction, and then we have a uniform stream plus dipole, and therefore we have flow like this. And the velocity at x equal to 0 is infinity, but that's okay. As I said, this is the inside of a circular cylinder. Okay, so we are only interested in flow outside. So as long as you impose the right boundary condition to determine B1, in this case, which is UA squared, then there is no flow coming out through this surface. Okay. So everything is contained. All the flow inside is really remain inside of circular cylinder. So therefore, the flow inside is completely separated from flow outside. that is true because we impose, boundary conditions correctly. Suppose we impose the, wrong boundary condition here, then we wouldn't get the, the closed line, closed, streamline. Okay. So once again, these are singularities, but that's okay because in r equal to 0 is not typically in the fluid domain. What else do I have to say? And also, so we looked at the case when n equal to 1, then I said this is a solution for dipole, and you can increase n from 1 to 2, 3, and so on. Those are all the multipoles. Okay, so this is source, dipole, and the multipoles. And if geometry is simple like this, then we only need the dipole. But if geometry is more complicated, then your phi has to be, so if suppose you have a velocity like this, then you have a uniform stream for sure, and then you need all the multipoles, and therefore you need and all other things here. Okay, and so since you have an infinite number of terms, it's not easy to determine all the coefficients analytically, and therefore you have to truncate it, and then you have to determine the B sub n and D sub n. And also when you have a flow like this, then you have to align dipole in the y direction. So in this case, uniform stream in the y direction. So I have to write uy plus ua squared divided by r sine theta. Okay. So this time the dipole is aligned in this way, and source is sitting here and sink is sitting here, although they are very infinitesimally close to each other. So if you change the sign, in other words, if you put a minus sign there, then you wouldn't get the circular cylinder. So basically that's what we went through last time. Any question so far? Okay, so next thing that we want to look at is this guy and this guy. So I said, A naught can be 0 because it's constant. When I take a derivative, this doesn't give you anything. And this time, we are looking at this potential or this potential. First of all, let's look at this potential. So phi is d naught theta log r. Okay. So that's the velocity potential that we have. And so when I take a radial velocity derivative, I end up with d phi dr, and which will give you d naught theta divided by r. Okay. On the other hand, the u theta, which is the azimuthal direction, the velocity in the azimuthal direction, then I have 1 over r d phi d theta. So when I take a theta derivative, I end up with 1 over r log r. So first of all, I have to worry about whether these velocity fields are finite at infinities, right? And this guy goes to 0 as r goes to infinity. because this one decays much faster than this, and therefore it goes to 0. So this one also goes to 0. Are these the acceptable? Are these physical solutions? Is this a physical solution? Or are these velocities are physical? As I said, these velocities are finite as r goes to infinity. So in that sense, it's physical, but it is not. The reason is, because I have theta here. Okay. The solution has to be periodic in theta, 2 pi periodic. So in other words, you have in plane, and this is r, and this is theta. So you fix r, and then you move around, right? And then you go back to exactly the same point, and then you should get exactly the same thing. But if you look at this radial velocity, when theta equal to 0, and when I go back, if theta becomes 2 pi, and then my velocity has been changed from 0 to 2 pi d naught divided by r. Okay? So even though I'm talking about the same point in the physical domain, my velocity has been changed, which is not allowed. So if I have a point, I should have only one velocity. So in that sense, this is not physical. Okay? Because it's not, since UR is not 2 pi periodic. So this guy is, this guy vanishes. We have to drop, that term. And the last term is when velocity potential is linear in theta. Phi is not 2 pi periodic. Okay? When I fix in r, when I go back to the original point, phi has been changed by 2 pi. But as I said, phi itself is not physical quantity. We introduce phi just for mathematics, because when I take a gradient, it gives us a velocity. So what we have to look at is velocity, which is the radial velocity and the tangential velocity. So it doesn't depend on r. So this is 0. But when you take a theta derivative with dividing by r, then I end up with C naught divided by r. So this solution, this velocity field look like similar to source, but this time radial velocity is 0 and tangential velocity is not equal to 0. For the source, we have a radial velocity which decays like 1 over r, but the tangential velocity was 0. Okay, and this time radial velocity is equal to 0, but tangential velocity is not. So when I draw a circle whose radius is r, then if I look at the point, and then I have a velocity which moves like this. Okay? So everything is rotating. if I draw another circle which is greater than before, then my velocity is smaller because it decays like 1 over r. Okay? But fluid particle is moving along the this circle. So even though phi is not 2 pi periodic, that's okay because velocity fields are 2 pi periodic. And this solution is called the vortex. So you shouldn't get confused. This vortex is different from vorticity. Vorticity is curl of velocity vector, right? That's the definition of vorticity, and this is a vortex. Okay. You might wonder whether I have a non-zero vorticity or not, because the fluid particles are moving, making a rotational motion. Okay. When you take the curl of this, do you expect zero or not? Non-zero? Any objection? Okay. The answer is 0. The reason is, these are velocity fields are obtained by taking gradient of velocity potential, right? So this is a representation of gradient in polar coordinates. So velocity field is always represented by gradient of some scalar function. So when you take a curl to find the vorticity, this is identically 0. Okay? So even though fluid particles are moving around, and the vorticity is identically 0. So it's still a rotational field. So if you draw a circle, the velocity field decays like, how do I draw this? So it's infinity, and then you have finite value, and then increase, like this. So it has to keep decreasing. So if this is origin, and it has to be infinity, and then it decays like this. So this is the tangential velocity in radius. So this is r, and this what I'm plotting is u theta. Okay. On the other hand, if there is the velocity field like this, in this case, the fluid particle is also rotating, but then this is not, the vorticity for this flow is not equal to 0, but vorticity for this guy is equal to 0. So that's a difference between rotational motion, rotational circular motion and rotational circular motion. Okay. So in general, we need to represent flow around the body. We need this term, this term, this term, and this term. And this term and this term with n equal to 1 represents the uniform flow in the x and y direction. And we have to drop this term because this term doesn't represent the physical solution because the velocity fields generated by this potential are not 2 pi periodic. Okay? So to represent the flow around the body, you need infinite number of terms, as I said, in general. So you put all the singularities at r equal to 0, then you can represent the flow around the body located at the origin. But that's not the only way to represent flow around the two-dimensional body. Okay, there are many different ways to do, and today I'm going to talk about distribution of sources along the x-axis. So this is related to your homework that I gave you for problem 2. So when I say source, I'm not just referring to the source with a positive volume flux. Can be negative volume flux. It has same form. The only difference between source and sink is the sign of the flux. So this time, instead of I have a one single source, I can have one source and one sink. Okay, but they are assumed they are apart. And then I have flow like this still, and this source, so it has to flow like this, correct? So I have a source here and sink here. If I put one source, one sink, but not dipole, because I put source and sink with a certain distance, and then I can generate flow like this. And then when I add the uniform stream, then I will end up with some closed body like this, and then flow around this body will be this. Okay? So by placing a source and sink, you can generate closed streamline like this. But unfortunately, the body that you generate would not be circle, and you don't know what kind of body you will generate in advance. But you do know if you have a source and sink with the same strength with opposite signs, then you can generate closed body when you put the uniform stream. But as I said, you don't know what the strength that you have to put to make certain geometry. Also, the geometry that you can make by just using source and sink is very limited. Okay, it's not general shape of body. So to represent general shape of body but symmetric, we use the distribution of So we use this kind of a distribution. And to be more specific, I can write in this way: 1 over 4 pi So this is a distribution of sources along the x-axis. So what you're looking at here is the following. So previously I wrote a source is given by capital Q divided by 2 pi log r, right? That's what I already wrote for source. And this time I have an integration of small q. So what I'm saying here is q dx is basically q. Okay. So I put a continuous distribution of sources. So I know if I have a source and sink, I have a closed body. And this time I have a continuous distribution of sources and sinks. Although I don't know the strength yet. Okay. And then you know, if I distribute, you know, source and sink correctly, then I have a chance to make a, you know, closed body. So to do that, we have to determine Q correctly. But this time, you know, I have a source here. I don't know what the sign of you know, Q. Some could be positive, some could be negative. Okay, and this x prime is the location of you know, each source, and the x prime represents, you know, that location. Okay. And then you integrate because you have a continuous distribution of sources. If you have only discrete, you know, finite number of sources and sinks, then you just do the summation, right? But this time I have a continuous distribution of sources. I, you know, take an interval. I have a 4 pi because I have a 1/2 here, and then I pull out. That's why I have 1/4 pi. And so if the source is sitting at the origin, I have x squared plus y squared, which is r squared. Since, you know, each source is located at different position, therefore I have x minus x prime. Okay, so x prime is the location because, you know, the sources are located at the x-axis. So y coordinate is always 0. But you can generate, you know, flow for only symmetric body because you are, you know, distribute, you know, sources on the axis. And then you integrate from minus L to L. That's the total length of body. Okay? The next question is, how do we find, you know, Q, the strength to represent the body that you want? In general, you know, you have to find, you know, numerically, but in the homework, you know, I asked you to use, you know, some approximation. So this, you know, thickness is much smaller than the length, and so everything you can impose boundary condition instead of on the body surface, you can impose it on the axis, right? That's what I said. So you find the approximate, you know, body boundary condition, then you impose body boundary condition on the axis. So to do that, what you need is d phi dy. Okay. So if I remember correctly, boundary condition looks like this, right? Something like this. Okay. I don't know if you looked at it or not. At y equals to 0. Okay. So what you need to do is to evaluate d phi dy, and then you make a connection between q and b of x. So let's do that. So d phi dy is given by 1/4 pi qx prime, and then I'm taking y derivative, and which is and 2y dx prime, correct? Integration is along this you know, the axis, and then you're going to impose boundary condition at y equal to 0. Because that's the boundary condition that you have to impose, where the boundary condition has to be imposed with an approximation. One thing you notice is that if you evaluate this function, this y derivative, vertical velocity, at y equal to 0, this guy is 0. Except when x is x prime. If this is 0, then you have 0 divided by 0. So you don't know what to do. But if x is not equal to x prime, or x prime is not equal to x, the way that you try to impose boundary condition, then if this is not 0, then this is 0. When I evaluate at y equal to 0. Okay? So what you need to do is, to take care of this part with carefully, okay? And that's the thing that I'm going to explain. So instead of y imposing boundary condition at y equal to 0, let's say I imposing at y equal to epsilon, and then I'm taking limit. Okay? But I'm not interested in the quantity when x is not equal to x prime. Because, when I take epsilon going to 0, this guy goes to 0. So what I have is the following. So I have a limit, epsilon going to 0. And then I have 1 over 2 pi. I pull out this guy outside. Because, I'm only interested in x prime equal to x. Otherwise, this term is 0 when I take epsilon going to 0 limit. Are you with me? I'm trying to evaluate this integral at y equal to 0. This is 0. If this is not equal to 0, then it's 0. So if x is not x prime, then this is 0, which is not interesting, or it's not of our interest. So I'm only interested in the case when x is equal to x prime, or near there. So let's say x plus x minus delta. So I'm looking at only the neighborhood of x prime equal to x. Away from this neighborhood, so x is sitting here, x prime changes. And when x prime is close to this point, then I could have a 0. Then I could have a non-zero integral. If my x prime is here, then this is not equal to 0. Therefore, this term is 0. So I'm not interested in that. So when x prime is close to this x point by delta, then this integral has some non-zero value. And there, this q, as an approximation, is just q of x instead of q of x prime, okay? Are you with me? No? So qx can change from x minus delta to x plus delta, okay? So as if you do the Taylor expansion, this is q of x minus delta q prime x and so on, right? Likewise, this guy gives qx plus delta q prime x. If delta, I can make delta as small as I wish, and then this guy will go away, and then this term and this term, all this function would be q of x. So that's why I can pull out, because it no longer depends on x prime. And then y is epsilon, so I have also I put 2 here. That's what I have. And then I have epsilon x minus x prime squared plus y squared, epsilon squared dx prime. Now I can integrate this, which is divided by 2 pi, and this is epsilon here, and then what I have here is 1 over epsilon times arctangent epsilon x prime minus x. Okay? So epsilon, this epsilon came from here. This epsilon coming from, integration of 1 over this. That gives, this. So this is arctangent. And this one cancels each other. And then what you end up with is the limit epsilon going to 0 and qx pi. And then we have arctangent delta divided by epsilon. So I have a same contribution from here to here. And that's why I multiply by 2. Okay, so the top one is delta minus. So this is an odd function, and therefore this will give you 2. Okay, from here. Then I take a limit as epsilon going to 0. What happens? This guy is infinity. Delta divided by 0 is infinity. So what is this? Arctangent infinity. I hope you know what the arctangent function is. So tangent is sine divided by cosine. So that goes to infinity. So tangent something goes to infinity. And that something has to be, this is sine divided by cosine. So cosine has to go to 0. So the first one is pi over 2. Okay? So this tells you infinity, and that will give me qx divided by 2. But this is true only when you go from top to bottom. So in other words, your epsilon is plus side. Okay? Then it's pi qx over 2. You can check if you go from bottom to top. So you can go this way or you can go this way, right? You can take a 0 limit from top to bottom. So if you take the other limit from the bottom, then you will get a minus qx divided by 2. So at the end, d phi dy at y 0, let me put plus and minus because it depends on whether you're going from here to here or here to here. Is equal to plus and minus qx divided by 2. Okay? So now originally you look at this problem. and you take the approximation. So you collect everything on the y-axis, on the x-axis, sorry. Okay. Then you impose boundary condition at the x-axis, and the boundary condition is written in terms of vertical velocity, and therefore you can determine q of x. So when you do your homework, check minus this part, minus part. Okay. In class I did the plus part. You go through minus part and make sure this is the case, and then you continue. So basically what happens, if you fix a position and then you have a source, that's what you expect, right? Vertical velocity, positive side here, negative side here. That's exactly what happens. Half of flux goes to up, half of flux goes down. This is a flux per unit length. So since I put in a source, then half goes up, half goes down, as we expect in the y direction. Okay. Of course, if q is negative, then we expect this. So inside of this body, in some part we will have you will have the sources, and in some part you will have a sink. Then you can represent the flow around this body approximately, as I said, because you use approximate body boundary condition. Otherwise, you have to find numerically. In the next homework, I'll ask you to find some numerical solution, but this time for this homework I want you to look at the approximate solution. But one more thing that I want to point out is, if you want to have a closed body, the total strength of source has to be the same as total strength of sink. If you have more flow, you have more outflow than inflow, then you wouldn't have a closed body. Okay. So to generate dipole, I need the same strength of source and sink, right? Then we can generate dipole, and we can put the source and sink with the same strength. Then we can have a closed body like this. But what if this guy has a much stronger strength than this? Flow going out, the sink doesn't have enough the capacity to hold it, then flow will go like this, and then you wouldn't have a closed streamline. So if you have some flow out from this source, then you should have the sink of same magnitude. So when you have a distribution, when you integrate the source strength, that has to be exactly the same as the strength of sink. So that's one check you can do. Okay? So you have enough information to do your homework in 2 days or in 1 day? I hope so. Otherwise, any question? Okay, sure.
You can also send the data to the
Yeah, but I don't have to take 0. I said I can make as small as I wish, but I'm saying neighborhood of x, I will have a non-zero contribution. Okay. And so I can take any limit I want, But I want, small delta because I want to pull this guy out from integration. That's the only, limitation or restriction on delta. Under that restriction, I can choose whatever I want. But I have to impose, boundary condition at or I equal to 0. That's why I take the limit. Because I have a 0, 0, that's why I take a limit. If I don't have that, then I don't have to take a limit. But I have to take a right limit. So when you take the limit, you have to look at it, carefully what is, the real limit that you want. In this case, this is the limit that I have to take. This is something arbitrary. But away from x, I wouldn't get any contribution anyway. So I have some flexibility for delta. Of course, this is all mathematics, but we are trying to find the mathematical solution of a Laplace equation, right? So, and we have to take a mathematical limit correctly to get the physical, something which physically meaningful. This is not the only way to show this. There are different ways to do. Okay, but I think this is one of the easiest way to show this. If you use contour, if you know contour integral in complex plane, then it's even easier. But you have to know the contour integral in complex plane. There, you don't have much ambiguity taking the limit, but okay. Any other question about homework? 여기서. pull out 됐냐고? The question is, how do I pull this guy out of integral? As I said, this guy, I can expand this guy with this. Right? I can keep doing it. So far I didn't make any assumption. Taylor expansion, if I add infinite number of terms, this is exactly this. So there is no approximation so far. I expand about x. That's why I put x prime here. X prime here. So now, when as I said, if x prime is far away from x, then this term is 0. So I don't care. Okay? So I'm only interested in neighborhood of x. When x prime is close to x, that's the only region that I'm interested in. So this guy is order of delta because x prime changes from here to here. Okay? So this, at most, this is the order of delta. Now I can make it as small as I wish. Then this is order delta. This is order delta squared, and so on. So these guys are, I would say, order of delta or smaller. Then I pull it out. If you want, right after you take this limit, take a delta goes to 0. You can do that. But it doesn't change anything, okay? So this is from Taylor expansion. And because we are interested in integration neighborhood of x. Otherwise, this integral is 0. So I can pull this out only when I integrate near x prime equal to x. Okay. Think about it. Okay. And any other question? We'll go through something similar a little later when we talk about panel method. And so I hope this time you are clear about this.
수사 생각 가지고 표현을 조용하는데 일반적으로 포텐셜을 전달할 거면 보면 다이폴도 같이 들어있는 이렇게 하나만.
Okay, the question is, why do we use, the source only when we use, panel method? I haven't talked about panel method yet, but basically what we are doing is when we have a, arbitrary geometry like this, then we represent, the solution by using, this continuous distribution of sources around the body surface, right? So this time, we assume this is symmetric. The body is symmetric, so we can, represent the flow, because symmetric flow by distributing, sources along the axis, right? That's what we can do. And suppose, the body is not symmetric, then by distributing sources only here, you cannot represent, non-symmetric, body. Okay? So in this case, you have to distribute, sources or things, depending on the sign, along the, body surface, then you determine the strength by imposing body boundary condition. That's a panel method that we are going to talk about a little later. The question is, why do we use, the source only instead of what? Can we, use, dipole or any other multiple? The answer is yes, you can use it. But there is a reason, mathematical reason why you want to use, the source only. I'll discuss that later, but in principle you can do it. In practice, it's very difficult to do. That's why we use, the source only. When we impose, body boundary condition, there is the equation that you have to solve. When you use, the source, then that equation is much easier to solve numerically than the other problem resulting from, the distribution of dipole. So we'll talk about that later. But in principle, you can use any, these are general solutions, so you can use any of these to represent the body. Yeah. But the main difficulty is, what is, the B sub n, C sub n, D sub n, right? Determination of that is a crucial thing. And you choose, right singularities, which gives, easier problem to solve. Any other question? Since I'm talking about 2D flow, so let me just briefly mention what the complex potential is in 2D. Complex potential is given by this. As a function of where z is x plus iy. So x is this axis, y is this axis. So this is a complex, function. Has a complex means it has a real and imaginary part. And this complex potential can be written in this way: velocity potential plus I stream function. remember that velocity potential satisfies Laplace equation, and stream function also satisfies Laplace equation for rotational flow. From definition, the vorticity is given by this. Laplace minus Laplacian of psi, probably you forgot by now, but when I talked about stream function, I talked about this. So this time you are looking at a rotational flow, so this guy is equal to 0, and then both velocity potential and stream function satisfy Laplace equation. Therefore, there is some connection between these two. Okay. So any velocity potential for any the singularity can be written in complex potential. So for example, for a source, f of z is q divided by 2 pi log z. For a dipole, f of z is I need a notation. What did I use for dipole? Z q. Do you have any letter that you want to write for strength of dipole? Mu? Although this has nothing to do with viscosity. That's what we usually use, but I do not want to make it confused. But this mu is not, the viscosity, okay? So there's some constant. So the complex potential for dipole is given by that. And for yeah. And then for here, q divided by 2r log z is x plus iy, right? And this is x cosine theta plus iy sine theta, r cosine theta plus ir sine theta. Because this is x, this is y. And then I can write this as r cosine theta plus I sine theta, meaning that this is r e to the I theta. Okay? So z is nothing but r e to the I theta. And then I have q divided by 2 pi log r plus q divided by 2 pi I here and theta. So meaning that this is phi and this is psi. So this is a phi for source and this is psi for source. I said, the streamlines are, lines of constant stream function. So let's say this is constant, meaning that theta is constant. So I can draw streamline easily. Fix theta, some angle, then constant theta. That's a streamline. Another constant theta, streamlines. This is streamline, this is streamline, this is streamline, this is streamline, this is streamline. For source. So this is psi is equal to 0. And this is psi equal to, let's say this is pi over 4. Then this has to be q divided by 2 pi times pi over 4. That's the streamline. And because I'm talking about source, the velocity vector always tangent to the streamlines. Okay? So these are the streamlines for a source. Okay, I'll talk about the dipole and the vortex on Thursday.